Imagine standing beneath a canopy of stars on a clear night, watching as light from distant galaxies reaches your eyes after traveling for millions of years through the vast emptiness of space. Each photon that touches your retina carries with it a story of time itself, a message from the past that somehow connects the deepest mysteries of our universe. Tonight, we embark on a journey that explores one of the most captivating questions in all of science. Could slowing light down actually open the door to time travel? Light is the fastest thing we know in our universe, racing through the vacuum of space at an incredible 299,792,458 meters per second. Nothing can move faster than this cosmic speed limit, and yet this very limitation might hold the key to unlocking something far more extraordinary than we ever imagined. Time, as we experience it in our daily lives, flows steadily forward like a river that never reverses its course. We age, seasons change, and moments slip away into memory, all following the relentless march of time's arrow. But what if this relationship between light and time is not as fixed as we believe? What if the speed at which light travels through space is not just a fundamental constant of physics, but actually a gateway to manipulating time itself? What if by learning to slow down light, we could somehow learn to slow down, stop, or even reverse the flow of time? These questions might sound like the stuff of science fiction, but they emerge from the very real and mind-bending discoveries of modern physics. Throughout the 20th century, brilliant minds like Albert Einstein revealed that space and time are not separate, independent entities, but are woven together into a single fabric called space-time. They showed us that time can stretch and contract, that it can run faster or slower depending on how fast you're moving or how strong the gravitational field around you happens to be. As we gaze up at those distant stars, their light carries more than just photons. It carries the profound possibility that by understanding and manipulating the speed of light, we might one day learn to navigate through time as easily as we navigate through space. Could the key to visiting the past or glimpsing the future lie hidden in our ability to control the very thing that illuminates our world? The idea that slowing light down could enable time travel challenges our most basic assumptions about reality. It suggests that time might not be the unchanging backdrop against which events play out, but rather a dynamic dimension that can be stretched, compressed, and perhaps even folded back upon itself. As we explore this fascinating possibility together, we will discover how the marriage of light and time in Einstein's theories opens doorways to possibilities that were once thought impossible. Tonight, we invite you to suspend your disbelief and join us on an exploration of the deepest mysteries of existence. We will journey through the strange world of relativity, where time dilates and space contracts. We will venture into the quantum realm, where particles can exist in multiple states simultaneously, and where the very act of observation changes reality. We will stand at the edge of black holes, where time itself seems to freeze, and we will contemplate the possibility that the universe might be far stranger and more malleable than we ever dared to imagine. So settle in, close your eyes if you wish, and let your mind wander through the cosmos as we explore the tantalizing possibility that slowing light down could be the first step toward mastering time itself. The journey we are about to take will challenge everything you thought you knew about the nature of reality, and by the end, you may find yourself looking at the world with entirely new eyes, seeing in every beam of sunlight and every twinkling star the potential keys to unlocking the greatest mystery of all, time travel. To understand how slowing light might unlock the secrets of time travel, we must first appreciate the profound significance of light speed in our universe. Light travels at exactly 299,792,458 meters per second through the vacuum of space. This is not just any ordinary number. It represents the ultimate speed limit of our universe, a cosmic boundary that nothing with mass can ever cross. Picture a single photon of light leaving the surface of our sun. In just 8 minutes and 20 seconds, that photon travels the 93 million mile journey through space to reach Earth, and perhaps enter your eye as you step outside on a sunny morning. The same photon that left the sun's surface before you finished your breakfast is now part of your visual experience of the world. This incredible journey happens at light speed, and it governs everything we know about cause and effect in our universe. But to truly appreciate the magnitude of this speed, let us put it into perspective. If you could travel at the speed of light, you could circle the entire Earth 7.5 times in just 1 second. You could travel from New York to London in about 20 milliseconds. You could reach the moon in 1.3 seconds and arrive at Mars in as little as 3 minutes when the planets are at their closest approach. The nearest star beyond our sun, Proxima Centauri, would take you just over 4 years to reach at light speed. Yet despite this incredible velocity, light speed is also intimately connected to the smallest scales of reality. Inside atoms, electrons orbit nuclei, and the electromagnetic forces that hold atoms together propagate at exactly the speed of light. The chemical bonds that make up your body, the electrical signals in your nervous system, the very forces that prevent you from falling through the floor, all operate at light speed. In a very real sense, the speed of light is woven into the fabric of your existence at every level. But why is the speed of light so important? The answer lies in one of the most revolutionary discoveries in the history of science. In 1905, a young patent clerk named Albert Einstein published a paper that would forever change our understanding of space and time. His special theory of relativity revealed that the speed of light is not just fast, it is the fundamental speed at which space and time themselves are connected. Einstein's breakthrough came from a simple but profound observation. The speed of light in a vacuum is the same for all observers, regardless of how fast they are moving. This might sound obvious, but it leads to consequences that defy our everyday intuition. If you are standing still and measure the speed of a beam of light, you will get exactly 299,792,458 meters per second. But if you are traveling at half the speed of light and measure that same beam, you will still get exactly 299,792,458 meters per second. This constancy of light speed means that something else must be variable. That something else turns out to be space and time themselves. Einstein showed us that space and time are not separate things, but are woven together into a single fabric called space-time. Imagine space-time as a vast, stretchy sheet, and everything in the universe from planets to people to particles exists within this sheet. The speed of light is like the maximum rate at which information can travel through this fabric. It sets the tempo for how quickly cause can lead to effect, how rapidly changes can propagate through the universe. This cosmic speed limit has profound implications for our understanding of time itself. When Einstein derived his famous equation E equals mc squared, he was revealing that mass and energy are interchangeable, and the speed of light squared is the conversion factor between them. But more importantly for our story, he was showing that time is not the fixed, unchanging river we once thought it was. Instead, time is elastic, capable of stretching and compressing depending on how fast you are moving relative to the speed of light. Consider what happens when you approach light speed. As you move faster and faster, something extraordinary occurs. Time begins to slow down relative to someone who is standing still. This is not science fiction. It is measurable reality. Particles in accelerators moving at 99% of light speed experience time dilation. Their internal clocks literally run slower than clocks in the laboratory. If you could somehow travel at 99.9% of light speed for what feels like 1 year to you, you would return to find that over 22 years had passed on Earth. This time, dilation effect becomes more and more dramatic as you approach light speed. At 99.99% of light speed, 1 year for you would equal over 70 years for everyone else. At 99.999% of light speed, that same year would stretch to over 200 years in the outside world. As you approach exactly light speed, time dilation approaches infinity. Time would essentially stop for you relative to the rest of the universe. The speed of light also determines how we experience causality itself. Nothing can travel faster than light, which means that causes must always precede their effects in a way that respects this cosmic speed limit. If something could travel faster than light, it would be possible to send signals into the past, potentially creating paradoxes where effects could precede their causes. This is why the speed of light is not just a speed limit for objects, but a fundamental limit on the flow of information itself. But here is where our story becomes truly fascinating. The speed of light that we measure, that fundamental constant that seems so fixed and immutable, might not be as constant as we think. In the early universe, some theories suggest that the speed of light might have been different. Cosmologists have proposed that in the first moments after the Big Bang, the speed of light could have been much higher than it is today, allowing distant regions of the universe to come into thermal equilibrium before light speed dropped to its current value. If the speed of light can change over cosmic time, then perhaps it can be changed by us, here and now, in controlled ways. This possibility opens up extraordinary avenues for manipulating the relationship between space and time. If we could create regions where light travels faster or slower than its normal vacuum speed, we might be able to create regions where time itself flows faster or slower. Scientists have already demonstrated that light can be slowed down dramatically when it passes through certain materials. In 1999, physicist Leanie Howe and her team at Harvard University managed to slow light down to just 17 meters per second, slower than a bicycle. They did this by passing light through an ultra-cold cloud of sodium atoms in a special quantum state called a Bose-Einstein condensate. This achievement was remarkable not just for the dramatic reduction in speed, but for what it revealed about the relationship between light and matter. The sodium atoms were cooled to temperatures just billionths of a degree above absolute zero, creating a state of matter where quantum effects dominate. In this exotic state, the atoms behave collectively as a single quantum entity, and they can interact with light in ways that seem to defy our everyday understanding of physics. Even more remarkably, scientists have managed to stop light completely, trapping it in clouds of atoms and then releasing it later without losing its information. In these experiments, a pulse of light enters the atomic cloud and becomes stored as a pattern of atomic excitations. The light ceases to exist as photons, but its information remains encoded in the quantum states of the atoms. Later, another pulse of light can retrieve this stored information, reconstructing the original light pulse and allowing it to continue on its way. If we can slow light down, stop it, and restart it, what does this mean for the flow of time itself? Could manipulating the speed of light in our local environment allow us to manipulate the flow of time around us? These questions push us into uncharted territory, where the boundaries between what is known and what is possible begin to blur. This is where the connection between light speed and time travel begins to emerge. If time dilation occurs when objects approach light speed, and if we can control the speed of light itself, then perhaps we can control the rate at which time flows. Perhaps by creating regions where light moves slower or faster, we could create regions where time moves slower or faster as well. The implications are staggering. Imagine a bubble of space where light has been slowed to a crawl. Would time inside that bubble also slow to a crawl? Could you step into such a region and experience time differently than the rest of the universe? Could you emerge from such a bubble to find that while minutes passed for you, hours or days passed for everyone else? These questions push us to the very edge of our understanding of physics. They challenge us to think about light not just as electromagnetic radiation that helps us see, but as the fundamental thread from which the fabric of space-time is woven. If we can learn to manipulate this thread, we might learn to manipulate the very structure of reality itself. The speed of light is more than just a measurement. It is the heartbeat of the universe, the rhythm that orchestrates the dance of space and time. Every process in the universe, from the fusion reactions in the cores of stars to the firing of neurons in your brain, operates according to the tempo set by light speed. It is the universal metronome that keeps the cosmic symphony in time. As we continue our journey into the mysteries of light and time, we will discover that this cosmic speed limit might not be a barrier to time travel, but rather the key that could unlock it. The more we understand light, the deeper we peer into the nature of time itself, and the closer we come to answering the ultimate question: can we really slow down light to unlock the secrets of time travel? Light travels faster than anything else in the universe. But what if this speed is not just a limit, but a bridge to understanding time itself? Time travel has captured human imagination for centuries, appearing in countless stories and dreams of adventure through the ages. But what was once purely the realm of fantasy has gradually emerged as a serious subject of scientific inquiry, thanks largely to our growing understanding of the relationship between light, space, and time. The theoretical foundations for time travel do not rest on magic or wishful thinking, but on the solid bedrock of Einstein's theories of relativity and the fundamental role that light speed plays in shaping the very fabric of reality. To understand how time travel might be possible, we must first recognize that time is not what it appears to be in our everyday experience. We tend to think of time as a steady river flowing in one direction, carrying us all along at the same rate from past to future. But Einstein's revolutionary insights revealed that time is far more flexible and mysterious than our intuitions suggest. Time can stretch like taffy, compress like a spring, and even come to a complete standstill under the right circumstances. The key to understanding this flexibility lies in recognizing that space and time are not separate entities, but are woven together into a single, four-dimensional fabric called space-time. Just as a piece of cloth can be stretched, twisted, or folded, space-time itself can be manipulated by mass, energy, and motion. The speed of light serves as the fundamental conversion factor between space and time, determining how changes in one dimension affect the other. When we talk about time travel in the context of physics, we are really talking about finding ways to navigate through this four-dimensional space-time in unexpected directions. Just as you can move forward, backward, left, right, up, or down through the three dimensions of space, the laws of physics suggest that under certain circumstances, you might be able to move backward or forward through the time dimension as well. The most straightforward form of time travel that physics allows is forward time travel through time dilation. This happens whenever you move at high speeds relative to someone else, or when you find yourself in a strong gravitational field. The closer you get to the speed of light, the more dramatically time slows down for you relative to the rest of the universe. This is not just a theoretical prediction. It is an observed reality that we measure in particle accelerators and account for in GPS satellites every day. Consider the famous twin paradox, one of the most elegant illustrations of relativistic time travel. Imagine identical twins, Alice and Bob. Alice boards a spacecraft capable of traveling at 99% of the speed of light and journeys to a nearby star system, while Bob remains on Earth. From Alice's perspective, inside the spacecraft, the journey might take just a few months. But when she returns to Earth, she discovers that Bob has aged many years. Alice has literally traveled into Earth's future by moving at speeds close to the speed of light. This effect becomes more dramatic as speeds approach closer and closer to light speed. At 99.9% of light speed, time dilation becomes so extreme that a journey lasting 1 year for the traveler would correspond to over 22 years passing on Earth. At 99.99% of light speed, that same year stretches to over 70 years in the outside world. The mathematics of relativity show that as velocity approaches exactly the speed of light, time dilation approaches infinity. But here is where our story takes an intriguing turn. What if we could manipulate the speed of light itself, rather than trying to accelerate objects to light speed? If the speed of light determines the rate of time dilation, then perhaps controlling light speed could give us direct control over the flow of time. This possibility opens up entirely new avenues for thinking about time travel that do not require the enormous energies needed to accelerate massive objects to relativistic speeds. The relationship between light speed and time is encoded in the very structure of space-time itself. Einstein's field equations, which describe how mass and energy curve space-time, contain the speed of light as a fundamental parameter. If we could somehow create regions where light travels at different speeds, we might be able to create corresponding regions where time flows at different rates. Imagine creating a bubble of space where light has been slowed to just a few meters per second. Inside this bubble, would time also slow to a crawl? The mathematical structure of relativity suggests that this might indeed be possible. Just as massive objects like black holes can slow down time by curving space-time, perhaps we could achieve similar effects by manipulating the local speed of light. This connection between light speed and time dilation extends beyond simple forward time travel. Some of the most exotic solutions to Einstein's field equations, such as closed time-like curves, wormholes, and Alcubierre warp drives, all involve regions where the normal relationship between space and time becomes twisted in unusual ways. In many of these scenarios, the behavior of light plays a crucial role in determining whether time travel is possible. Closed time-like curves are paths through space-time that loop back on themselves, allowing a traveler to return to their own past. These mathematical solutions exist within Einstein's theory, though whether they could exist in reality remains hotly debated. What makes these curves possible is the extreme warping of space-time, which can occur when energy densities become very large or when exotic forms of matter with negative energy density are present. Wormholes represent another fascinating possibility for time travel. These theoretical tunnels through space-time could potentially connect different regions of space and time, allowing for rapid travel across vast distances or even into the past. But keeping a wormhole open and traversable would likely require exotic matter, with properties that seem to violate our normal understanding of physics. The speed of light plays a crucial role in determining the stability and traversability of these hypothetical structures. The Alcubierre warp drive, proposed by physicist Miguel Alcubierre in 1994, offers yet another approach to faster-than-light travel that could enable time travel. Rather than accelerating a spacecraft to light speed, the Alcubierre drive would contract space-time in front of the ship and expand it behind, allowing the ship to surf on a wave of warped space-time. While the ship itself would never exceed light speed locally, it could effectively travel faster than light by riding this wave of compressed and expanded space. All of these exotic possibilities share a common thread. They involve manipulating the fundamental structure of space-time in ways that alter the normal relationship between space and time. And in each case, the speed of light serves as the crucial parameter that determines how these manipulations affect the flow of time. But perhaps the most intriguing possibility is that we might not need to invoke exotic matter or extreme energies to achieve time travel effects. If we can learn to control the speed of light directly, we might be able to create time dilation effects using much more modest means. The experiments that have successfully slowed light to bicycle speeds, or even stopped it, completely suggest that we already possess some of the tools needed to manipulate the relationship between light and time. Recent advances in quantum optics and metamaterials have opened up new possibilities for controlling light in unprecedented ways. Scientists have created materials with negative refractive indices that cause light to bend in unusual directions. They have developed techniques for cloaking objects by bending light around them. They have even created materials that can make light appear to travel backward in time over short distances. These achievements hint at a future where we might have much more sophisticated control over the behavior of light. If we can already slow light down, speed it up, stop it, and make it bend in unnatural ways, then perhaps we are not so far from being able to create regions where the local speed of light is dramatically different from its normal vacuum value. And if we can do that, then perhaps we can create regions where time itself flows at different rates. The implications of such control would extend far beyond simple time travel. We might be able to create temporal laboratories where chemical reactions could be slowed down to study them in unprecedented detail. We might develop medical technologies that could slow down biological processes during surgery or healing. We might even be able to create temporal havens where people could experience extended lifespans by living in regions where time flows more slowly. The theoretical foundation for time travel through light manipulation rests on solid scientific ground. The mathematics of relativity clearly show that time and space are interconnected through the speed of light. Experiments have demonstrated that we can already control light speed in dramatic ways. The next step is to understand how these laboratory demonstrations might be scaled up and applied to manipulate the flow of time itself. As we delve deeper into these possibilities, we begin to see that time travel may not require the exotic conditions found near black holes or the enormous energies of particle accelerators. Instead, it might be achieved through the careful manipulation of light itself, using techniques that are already within our scientific grasp. The key lies in understanding that light is not just something that helps us see the world, but is literally the medium through which space and time are connected. By learning to control this medium, we might learn to control time itself. Time travel remains a speculative dream, but could changing the speed of light bring us closer to making it a reality? The dream of slowing down light was once considered impossible, a violation of one of nature's most fundamental constants. Light, after all, is supposed to travel at exactly 299,792,458 meters per second through empty space, never faster, never slower. This cosmic speed limit seemed as unchangeable as the laws of mathematics themselves. Yet in the last few decades, scientists have achieved something that would have seemed like pure magic to earlier generations. They have learned to slow light down, to stop it completely, and even to make it behave in ways that challenge our most basic understanding of physics. The journey toward controlling light speed began with a deeper understanding of how light interacts with matter. When light travels through any material denser than vacuum, it slows down. This is why a straw appears bent when placed in a glass of water, and why diamonds sparkle with such brilliant fire. The speed of light in a material is characterized by something called the refractive index, which tells us how much slower light travels in that material compared to its speed in vacuum. In ordinary glass, light travels at about 200 million meters per second, roughly 2/3 of its vacuum speed. In water, light moves at about 225 million meters per second, about 3/4 of its vacuum speed. In diamond, one of the most optically dense common materials, light crawls along at only 124 million meters per second, less than half its vacuum speed. These reductions in speed, while significant, are still enormous by everyday standards. But what if we could slow light down much more dramatically? What if we could reduce its speed not by a factor of 2 or 3, but by factors of millions or billions? This seemed impossible until scientists began exploring the exotic quantum states of matter that exist at temperatures close to absolute zero, where the normal rules of physics begin to break down and quantum mechanical effects take over. The breakthrough came in 1999 when physicist Lena Howe and her team at Harvard University achieved something unprecedented. Working with a cloud of sodium atoms, cooled to just 50 billionths of a degree above absolute zero, they managed to slow a pulse of light down to just 17 meters per second. To put this in perspective, that is slower than a bicycle, slower than you can run, slow enough that you could theoretically keep pace with the light beam on foot. The key to this remarkable achievement was creating what physicists call a Bose-Einstein condensate, a state of matter that exists only at temperatures so cold that individual atoms lose their separate identities and begin to behave as a single, coherent quantum entity. In this ultra-cold cloud of sodium atoms, the normal electromagnetic properties that govern how light interacts with matter become dramatically enhanced, allowing the atoms to grab onto light pulses and slow them down to a crawl. The technique works by using a control laser beam to modify the quantum properties of the sodium atoms, creating what physicists call electromagnetically induced transparency. Normally, the sodium atoms would absorb light at certain frequencies, making the cloud opaque. But by carefully tuning the control laser, the researchers can create quantum interference effects that make the cloud transparent, while simultaneously giving it extraordinary powers to slow down light. In this altered state, the sodium atoms act like a series of quantum speed bumps, repeatedly absorbing and re-emitting the light photons in a coordinated dance that preserves the light's information while dramatically reducing its speed. The light pulse becomes intimately entangled with the quantum states of the atoms, creating a hybrid entity that is part light and part matter. Even more remarkably, Howe's team later demonstrated that they could stop light completely, bringing a light pulse to a complete halt inside the atomic cloud, and then restarting it later without losing any of its original information. In these experiments, the light pulse enters the cloud and becomes completely converted into a pattern of atomic excitations. The photons cease to exist as particles of light, but their information remains encoded in the quantum states of the atoms, like a message written in the language of quantum mechanics. This storage process can last for extended periods, allowing the light to remain frozen in time while the world continues around it. When the researchers are ready, they can use another laser pulse to read out the stored information and reconstruct the original light pulse, which then continues on its way as if nothing had happened. It is as if time itself has been paused for the light, creating a pocket of frozen temporal flow in an otherwise dynamic universe. But the implications of these experiments extend far beyond the mere novelty of slow light. If we can control the speed of light so dramatically, what does this mean for the flow of time itself? According to Einstein's theory of relativity, space and time are intimately connected through the speed of light. When we change one, we might expect to change the other as well. Consider what happens inside the ultra-cold atomic cloud, where light has been slowed to bicycle speeds. From the perspective of relativity, this region of space has effectively become a zone where the local speed of light is dramatically reduced. If the mathematics of space-time are to be believed, this should also be a region where time flows differently than in the surrounding space. The relationship between light speed and time flow is encoded in the fundamental structure of Einstein's equations. When light slows down in a medium, it is not just the photons that are affected, but potentially the entire causal structure of space-time in that region. Events that would normally be separated by tiny fractions of a second might now be stretched out over much longer intervals, creating a zone of slow time surrounding the slow light. This possibility opens up extraordinary avenues for practical time manipulation. Imagine scaling up these slow light experiments to create macroscopic regions where time flows at a different rate than the surrounding world. You could step into such a region and experience time differently, living through hours or days while only minutes pass in the outside world. Alternatively, you could create a zone of accelerated time where you could observe slow processes like plant growth or healing in fast forward. The potential applications are mind-boggling. Medical procedures could be performed in slow time zones where surgeons would have effectively unlimited time to work with precision. Chemical reactions could be studied in unprecedented detail by slowing them down to observable speeds. Biological processes could be accelerated or decelerated to aid in research or healing. Computer calculations could be performed in fast time zones to achieve speeds that would otherwise require enormous increases in processing power. But creating these macroscopic time zones would require overcoming significant technical challenges. The current slow light experiments work only with very specific wavelengths of light and require incredibly precise conditions to maintain the quantum states necessary for electromagnetically induced transparency. Scaling these effects up to influence larger regions of space would require new approaches and potentially new physics. One promising avenue involves the use of metamaterials, artificially structured materials designed to have electromagnetic properties not found in nature. These materials can be engineered to have negative refractive indices, causing light to bend in unusual directions, or to have refractive indices that can be electrically controlled, allowing for dynamic manipulation of light speed. Researchers have already created metamaterials that can cloak objects by bending light around them, making them effectively invisible. They have developed materials that can focus light beyond the normal diffraction limit, achieving resolution previously thought impossible. They have even created structures that can make light appear to travel backward in time over very short distances, at least from the perspective of certain measurements. These achievements suggest that we are only beginning to scratch the surface of what might be possible with advanced control over electromagnetic fields. As our understanding of metamaterials and quantum optics continues to advance, we may develop the ability to create regions where light behaves in ways that would fundamentally alter the local flow of time. Another approach involves using intense electromagnetic fields to modify the vacuum itself. According to quantum field theory, empty space is not really empty, but is filled with virtual particles that pop in and out of existence on timescales too short to observe directly. These quantum fluctuations give the vacuum its own electromagnetic properties, and in principle, these properties could be modified by strong fields. Some theoretical proposals suggest that sufficiently intense laser fields could alter the effective speed of light in vacuum itself, creating regions where photons travel faster or slower than their normal vacuum speed. While the energy requirements for such effects are currently far beyond our technological capabilities, they represent tantalizing possibilities for future advances. The quest to slow down light has already yielded remarkable results that were unimaginable just a few decades ago. We have learned to stop time for photons, to store light like information in a computer memory, and to control electromagnetic fields with unprecedented precision. Each of these achievements brings us closer to the ultimate goal of manipulating the flow of time itself. The experiments that have slowed light to bicycle speeds are just the beginning. As we develop more sophisticated techniques for controlling light-matter interactions, we may find that the boundary between manipulating light and manipulating time becomes increasingly blurred. The dream of time travel may not require the exotic conditions near black holes or the enormous energies of relativistic spacecraft. Instead, it might be achieved through the careful application of quantum optics and electromagnetic engineering, using techniques that are already within our grasp. Could slowing light lead to something more profound than just an experiment in physics? What if it could alter the flow of time itself? Time dilation stands as one of the most profound and counterintuitive discoveries in the history of science, revealing that time itself is not the fixed, unchanging backdrop we once believed it to be. Instead, time is malleable, stretchy, and intimately connected to motion and gravity through the fundamental constant we call the speed of light. This connection between light and time is not merely theoretical, but has been measured, verified, and even exploited in technologies we use every day. Understanding how light affects our perception and experience of time opens doorways to comprehending how we might one day manipulate time itself. The story of time dilation begins with Einstein's revolutionary insight that nothing can travel faster than light, and that the speed of light remains constant for all observers, regardless of their motion. This seemingly simple statement has consequences that shatter our everyday understanding of reality. When you approach the speed of light, something extraordinary happens. Time begins to slow down for you relative to everyone else in the universe. This is not an illusion or a trick of perception. Time literally flows more slowly when you move at high speeds. To understand this effect, imagine watching a clock as you accelerate toward the speed of light. From your perspective, inside your high-speed reference frame, the clock appears to tick normally. 1 second follows another in the familiar rhythm you have known your entire life. But to an observer watching you from a stationary position, your clock appears to run slower and slower as your speed increases. At 90% of light speed, your clock would appear to run at less than half its normal rate. At 99% of light speed, it would crawl along at just 1/7 of its normal pace. This time dilation effect becomes more dramatic as speeds approach closer to the speed of light. At 99.9% of light speed, time slows down by a factor of over 22. This means that if you spent what feels like 1 year traveling at this incredible velocity, over 22 years would pass for everyone else. At 99.99% of light speed, the dilation factor grows to over 70. Your single year of travel would correspond to more than 7 decades passing in the outside world. The mathematics of special relativity show that, as velocity approaches exactly the speed of light, time dilation approaches infinity. Time would essentially stop for you relative to the rest of the universe. But massive objects can never actually reach light speed, as doing so would require infinite energy. This is why light itself, composed of massless photons, can travel at the cosmic speed limit, while everything else must fall short. These effects are not merely theoretical curiosities. Time dilation is measured and confirmed in particle accelerators around the world every day. Subatomic particles called muons, created when cosmic rays strike Earth's atmosphere, provide a natural demonstration of relativistic time dilation. These particles have very short lifetimes, normally decaying in just 2.2 microseconds. At such brief lifespans, muons created high in the atmosphere should decay long before reaching Earth's surface, even traveling at near light speed. Yet muons are routinely detected at ground level, and the reason is time dilation. The muons are moving so fast that time slows down for them relative to Earth. From the muon's perspective, its lifetime is still 2.2 microseconds, but from Earth's perspective, the muon lives much longer because its internal clock is running slow. This allows muons time to complete their journey from the upper atmosphere to the ground before decaying. Global Positioning System satellites provide another everyday example of time dilation at work. These satellites orbit Earth at speeds of about 14,000 kilometers per hour, fast enough to produce measurable time dilation effects. The atomic clocks aboard GPS satellites run slightly slow compared to identical clocks on Earth's surface. Without corrections for this relativistic effect, GPS navigation would become increasingly inaccurate over time, with errors accumulating at a rate of about 10 kilometers per day. But time dilation is not limited to high-speed motion. Einstein's general theory of relativity revealed that gravity also affects the flow of time. Clocks run slower in stronger gravitational fields, an effect called gravitational time dilation. This means that time flows slightly faster at the top of a skyscraper than at ground level, and slightly faster in orbit than on Earth's surface. GPS satellites experience both kinematic time dilation from their orbital motion and gravitational time dilation from being higher in Earth's gravitational field. These gravitational effects on time become more extreme near massive objects. Close to a black hole, where gravity becomes incredibly strong, time dilation reaches dramatic proportions. An astronaut falling toward a black hole would experience time normally from their own perspective, but to an outside observer, the astronaut's clocks would appear to slow down more and more as they approached the black hole's event horizon. Near the event horizon, time would appear to nearly stop from the outside observer's perspective. The connection between light and time dilation becomes especially fascinating when we consider what happens to light itself in these extreme environments. Near a black hole, light trying to escape the intense gravitational field becomes redshifted, its wavelength stretched to longer, redder colors. This gravitational redshift is essentially a manifestation of time dilation. The light is not just changing color, it is experiencing the warped flow of time near the black hole. This intimate relationship between light and time suggests profound possibilities for manipulating time through the control of light. If gravity can slow down time by affecting how light travels through curved space-time, perhaps we could achieve similar effects by directly manipulating the speed and behavior of light itself. The experiments that have slowed light to bicycle speeds hint at this possibility. Consider what time dilation might mean inside a region where light has been dramatically slowed. If light can be reduced to just 17 meters per second, as demonstrated in Lin Hao's experiments, what happens to the flow of time in that region? The mathematics of relativity suggests that where light speed is reduced, time flow should be affected as well. A region of slow light might also be a region of slow time. This possibility opens up extraordinary scenarios for practical time manipulation. Imagine stepping into a chamber where light has been slowed to a crawl. Inside this chamber, time itself might flow more slowly relative to the outside world. You could spend hours or days inside while only minutes pass outside. From your perspective, everything would seem normal, but when you emerged, you would discover that you had effectively traveled into the future. The implications extend beyond simple time travel. Such controlled time dilation could revolutionize scientific research, medical procedures, and human experience itself. Chemical reactions could be studied in slow motion by conducting them in regions of slowed time. Surgical procedures could be performed with unlimited precision by working in chambers where time flows slowly for the surgeon, but normally for monitoring equipment outside. Biological processes could be manipulated by exposing living organisms to regions of altered time flow. Perhaps aging could be slowed by spending time in slow time regions, or healing could be accelerated by using regions where time flows faster. The possibilities are limited only by our imagination and our technical ability to create and control these temporal environments. But creating macroscopic regions of controlled time dilation would require advances beyond current slow light experiments. The quantum states necessary for dramatically slowing light are extremely fragile and difficult to maintain. Scaling these effects up to influence human-sized regions would require new approaches and potentially new physics. One possibility involves using the extreme time dilation effects near black holes or other massive objects. While we cannot create black holes in the laboratory, we might be able to simulate their effects using intense electromagnetic fields or exotic matter. Theoretical proposals for time machines often involve creating closed loops in space-time using rotating cylinders of ultra-dense matter or traversable wormholes stabilized by exotic matter with negative energy density. Another approach might involve manipulating the quantum vacuum itself. According to quantum field theory, empty space is filled with virtual particles constantly popping in and out of existence. These quantum fluctuations give vacuum its electromagnetic properties, and in principle, these properties might be modified by intense fields. Some theories suggest that sufficiently powerful lasers could alter the effective speed of light in vacuum, creating regions where time flows differently. The relationship between light and time becomes even more intriguing when we consider quantum mechanical effects. In the quantum world, particles can exist in superposition states, being in multiple places, or having multiple velocities simultaneously. Quantum entanglement allows particles to influence each other instantaneously across vast distances, seemingly violating the speed of light limit for information transfer. These quantum phenomena suggest that our understanding of light, time, and causality may be incomplete. Perhaps there are quantum mechanical pathways to time travel that do not require the extreme energies or exotic matter of classical general relativity. Quantum tunneling allows particles to pass through barriers that should be impenetrable according to classical physics. Might there be temporal barriers that could be tunneled through as well? Recent experiments in quantum optics have demonstrated increasingly sophisticated control over light-matter interactions. Scientists have created quantum states of light that exist in superposition, being in multiple places simultaneously. They have generated entangled photons that remain connected across large distances. They have even demonstrated quantum teleportation, transferring the quantum state of one particle to another without the particles themselves traveling through the intervening space. These quantum control techniques might eventually be applied to manipulate the relationship between light and time in ways we are only beginning to understand. Perhaps quantum superposition could be used to create light that exists at multiple speeds simultaneously, generating correspondingly complex time dilation effects. Quantum entanglement might allow for instantaneous coordination of time flow across separated regions of space. The study of time dilation has revealed that time is far more flexible and mysterious than our everyday experience suggests. The speed of light serves as the fundamental constant that governs how time can be stretched, compressed, and warped by motion and gravity. As our ability to control light becomes more sophisticated, we edge closer to the possibility of controlling time itself. The experiments that have demonstrated dramatic slowing of light represent early steps toward this ultimate goal. While we cannot yet create human-scale regions of altered time flow, we have proven that the speed of light is not as fixed as once believed. We have shown that light can be stopped, stored, and restarted, opening possibilities for manipulating the temporal structure of space-time itself. At the edge of light speed, time bends and stretches in unexpected ways. Could manipulating light allow us to control this distortion? In the realm of quantum mechanics, light reveals its most mysterious and counterintuitive nature, existing as both wave and particle in a strange dance that defies our everyday understanding of reality. This quantum nature of light opens up possibilities for time manipulation that go far beyond the classical physics of relativity, suggesting that the key to time travel might lie not in the realm of massive spacecraft or exotic matter, but in the subtle quantum properties of photons themselves. As we delve deeper into the quantum world, we discover that light possesses abilities that seem almost magical, abilities that might one day be harnessed to bend time itself. The quantum revolution began in the early 20th century, when scientists discovered that light, which had been understood as a wave for over a century, also behaves like a stream of particles called photons. This wave-particle duality is not merely an abstract concept, but a fundamental feature of reality that has been confirmed in countless experiments. a single photon can interfere with itself, passing through multiple paths simultaneously and creating interference patterns that reveal its wave-like nature. Yet when we try to detect which path the photon took, it behaves like a discrete particle, forcing us to confront the strange reality that light exists in multiple states until the moment we observe it. This quantum behavior becomes even more mysterious when we consider photons in isolation. A single photon can exist in what physicists call a superposition state, being in multiple places, having multiple energies, or traveling in multiple directions simultaneously. Only when we make a measurement does the photon collapse into a definite state, choosing one reality from among many possibilities. This collapse of the quantum wave function happens instantaneously, suggesting a connection between consciousness, observation, and the fundamental nature of reality. The implications of quantum superposition for time travel are profound. If a photon can exist in multiple states simultaneously, perhaps it can also exist at multiple times simultaneously. Quantum experiments have demonstrated that photons can be prepared in superposition states of different energies, corresponding to different frequencies and wavelengths. Since energy and frequency are related to time through Planck's constant, these energy superpositions might represent a form of temporal superposition, where the photon exists across multiple moments of time. Even more intriguing is the phenomenon of quantum entanglement, where two or more photons become connected in such a way that measuring one instantly affects the others, regardless of the distance separating them. Einstein famously called this spooky action at a distance, and initially rejected it as impossible. But decades of experiments have confirmed that entanglement is real, and that information about quantum states can be shared between entangled particles faster than light could travel between them. This apparent violation of the speed of light limit raises fascinating questions about the nature of time and causality. If entangled photons can influence each other instantaneously across vast distances, are they operating outside the normal flow of time? Some interpretations of quantum mechanics suggest that entangled particles exist in a timeless realm where past, present, and future are not clearly defined. Perhaps by manipulating quantum entanglement, we could access this timeless realm and use it as a pathway for time travel. Recent experiments have pushed the boundaries of quantum entanglement even further. Scientists have created entangled photons that remain connected across hundreds of kilometers, demonstrating quantum communication links that could form the basis of a quantum internet. They have entangled not just the properties of photons, but their orbital angular momentum, creating twisted beams of light that carry information in their corkscrew-shaped wavefronts. More remarkably, researchers have achieved quantum teleportation, transferring the complete quantum state of one photon to another without the original photon traveling through the intervening space. In these experiments, the quantum information seems to disappear from one location and instantly appear at another, as if it has traveled through some hidden dimension that bypasses normal space and time. While no actual matter is transported in quantum teleportation, the phenomenon suggests that information itself might be able to move through pathways that transcend our ordinary understanding of space-time. The quantum vacuum, once thought to be empty space, has revealed itself to be a seething ocean of virtual particles constantly popping in and out of existence. These quantum fluctuations occur on timescales so brief that the particles cannot be directly observed, but their effects can be measured through phenomena like the Casimir effect, where metal plates placed very close together experience a tiny attractive force due to the pressure of virtual photons in the vacuum between them. This quantum foam, as it is sometimes called, suggests that space and time themselves might have a granular structure at the smallest scales. If time is not continuous, but comes in discrete quantum units, then perhaps there are quantum mechanical shortcuts through time that bypass the normal flow of causality. Virtual particles that exist for less than the time it would take light to travel their own wavelength seem to operate outside the normal constraints of relativity. Perhaps, by learning to manipulate these quantum processes, we could find ways to step outside the normal flow of time. Quantum field theory predicts even more exotic possibilities. In extremely intense electromagnetic fields, the quantum vacuum itself can be polarized, creating virtual electron-positron pairs that affect the propagation of light. Some theoretical calculations suggest that sufficiently powerful laser pulses could modify the effective speed of light in vacuum by altering these quantum fluctuations. While the energies required are far beyond current technology, these predictions hint at fundamental connections between quantum mechanics and the structure of space-time. The phenomenon of quantum tunneling provides another intriguing avenue for exploring quantum time travel. In quantum tunneling, particles can pass through energy barriers that should be impenetrable according to classical physics. The particle does not go over or around the barrier, but simply appears on the other side, as if the barrier did not exist. Measurements of tunneling times have yielded puzzling results, with some experiments suggesting that particles tunnel through barriers instantaneously, while others indicate that the tunneling process takes a finite but very small amount of time. If particles can tunnel through energy barriers, perhaps they can also tunnel through temporal barriers. Some theoretical proposals suggest that virtual particles in the quantum vacuum might be able to tunnel backward in time over very short intervals, creating closed, time-like curves at the quantum scale. While these effects would be incredibly tiny and brief, they might represent the fundamental mechanism by which time travel could be achieved. The concept of quantum coherence adds another layer of mystery to the quantum nature of light. When photons are prepared in coherent states, they can maintain their quantum properties over extended periods and distances. Laser light is a form of coherent photons, where millions of photons all oscillate in perfect synchronization. This coherence allows for interference effects and quantum correlations that would be impossible with incoherent light. Recent advances in quantum optics have demonstrated increasingly sophisticated forms of coherence control. Scientists have created squeezed light states where the quantum uncertainty is redistributed, making certain measurements more precise at the expense of others. They have generated light with negative dispersion, where shorter wavelengths travel faster than longer ones, the opposite of what normally occurs. They have even created light pulses that appear to travel backward in time over very short distances, at least from the perspective of certain measurement techniques. These achievements hint at possibilities for manipulating the quantum properties of light in ways that could affect the flow of time. If quantum coherence can be maintained and controlled over macroscopic scales, perhaps we could create regions where the quantum nature of light generates measurable effects on temporal flow. Imagine a chamber filled with carefully prepared coherent photons, all existing in quantum superposition states that span multiple moments of time. Could such a system create a macroscopic superposition of different temporal states? The quantum Zeno effect provides another fascinating connection between quantum mechanics and time. This effect occurs when repeated quantum measurements slow down or even prevent the evolution of a quantum system. By observing a quantum particle frequently enough, its natural evolution can be frozen, as if time itself has been stopped for that particle. This suggests that the act of measurement, and perhaps consciousness itself, plays a fundamental role in the flow of time at the quantum level. Some interpretations of quantum mechanics, such as the many worlds theory, suggest that every quantum measurement creates a branching of reality into multiple parallel universes. In this view, all possible outcomes of every quantum event actually occur, but in separate branches of an ever-expanding multiverse. If this interpretation is correct, then perhaps time travel is not about moving through time within a single universe, but about finding ways to move between different branches of the quantum multiverse. The The delayed choice quantum eraser experiments have demonstrated that decisions made in the present can appear to retroactively affect events in the past. In these experiments, photons are prepared in entangled states and sent along different paths. The decision of whether to erase information about which path each photon took can be made after the photons have already been detected. Yet this future decision affects the interference patterns observed in the past detection events. While these results do not violate causality in any practical sense, they do suggest that the quantum world operates according to principles that transcend our ordinary understanding of time. As our ability to manipulate quantum systems becomes more sophisticated, we are discovering new ways that quantum mechanics might enable forms of time travel that were never imagined by classical physics. Quantum computation uses the superposition and entanglement properties of quantum systems to perform calculations that would be impossible with classical computers. Perhaps quantum temporal computers could perform calculations that span multiple moments of time, using the past and future as computational resources. The study of quantum consciousness suggests that our brains might operate as quantum systems, using coherence and entanglement to process information in ways that classical neural networks cannot explain. If consciousness has quantum properties, and if quantum systems can transcend ordinary temporal boundaries, then perhaps consciousness itself has some ability to navigate through time in ways we are only beginning to understand. Recent developments in quantum biology have revealed that living systems routinely exploit quantum effects for biological functions. Photosynthesis in plants uses quantum coherence to efficiently transfer energy from light harvesting complexes to reaction centers. Bird navigation appears to rely on quantum entanglement in specialized proteins that can sense magnetic fields. These discoveries suggest that the boundary between the quantum and classical worlds is not as sharp as once believed, and that quantum effects might be more accessible to macroscopic manipulation than previously thought. The quantum nature of light opens up possibilities for time travel that go far beyond the classical approaches of relativity. While we cannot yet create macroscopic quantum states that span multiple times, we have demonstrated increasingly sophisticated control over the quantum properties of photons. Each advance in quantum optics brings us closer to understanding how the fundamental quantum nature of reality might be harnessed to transcend the ordinary limitations of space and time. In the quantum realm, the boundaries between time and light blur. Could this be where time travel becomes possible? Space-time is perhaps the most profound and beautiful concept in all of physics, revealing that the universe is not merely a stage upon which events unfold, but is itself a dynamic, malleable entity that participates in every cosmic drama. This four-dimensional fabric, woven from the threads of space and time, responds to the presence of matter and energy by curving and warping in ways that guide the motion of everything from photons to planets. At the heart of this cosmic tapestry lies the speed of light, serving as both the fundamental unit of measurement and the ultimate speed limit that governs how information and causality can flow through the universe. To understand how the speed of light shapes the fabric of space-time, we must first appreciate the revolutionary nature of Einstein's insight. Before relativity, space and time were considered separate and absolute. Space was the unchanging three-dimensional stage upon which events occurred, and time was the universal clock that ticked away at the same rate for everyone in the universe. But Einstein realized that this separation was an illusion, a consequence of our limited perspective from within a single reference frame moving at speeds far below the speed of light. The true reality is that space and time are intimately connected, forming a unified four-dimensional continuum where the speed of light serves as the conversion factor between spatial and temporal dimensions. Just as you can trade off distance in one spatial direction for distance in another while keeping the total distance constant, You can trade off intervals in space for intervals in time, while keeping the space-time interval constant. This space-time interval, measured in units where the speed of light equals 1, remains the same for all observers regardless of their motion. This unification of space and time has profound implications for how we understand the propagation of light and its relationship to causality. Light always travels along what physicists call null geodesics, paths through space-time where the space-time interval is exactly 0. This means that from the perspective of a photon, no time passes during its journey, regardless of how far it travels through space. A photon leaving a distant galaxy billions of years ago experiences no passage of time during its journey to Earth. In a very real sense, the photon exists outside of time, connecting distant events across the universe in an eternal present moment. The curvature of space-time around massive objects provides one of the most striking demonstrations of how matter and energy can affect the fabric of reality itself. When Einstein first proposed that massive objects curve space-time, it seemed like an abstract mathematical concept. But observations of light bending around the sun during solar eclipses, the precession of Mercury's orbit, and the discovery of gravitational lensing have confirmed that space-time curvature is a measurable reality. Near a massive object like the sun, space-time curves in such a way that the shortest path between 2 points is no longer a straight line in ordinary space, but a curved path that follows the geometry of the warped space-time. Light, always following the shortest path through space-time, appears to bend as it passes near massive objects. This gravitational lensing effect has become a powerful tool for astronomers, allowing them to observe distant galaxies that would otherwise be hidden behind closer objects. The curvature of space-time also affects the flow of time itself. Clocks run slower in regions where space-time is more strongly curved, an effect called gravitational time dilation. Near the surface of the Earth, this effect is tiny but measurable. Atomic clocks at different altitudes tick at slightly different rates, with higher clocks running faster than lower ones. But near extremely massive objects like neutron stars or black holes, gravitational time dilation becomes dramatically pronounced. Consider what happens to light and time near a black hole, one of the most extreme examples of space-time curvature in the universe. As matter falls into a black hole, space-time becomes increasingly warped until it reaches a point of no return called the event horizon. At this boundary, space-time curvature becomes so extreme that even light cannot escape. From the perspective of an outside observer, time appears to slow down more and more as objects approach the event horizon, until time seems to stop completely at the boundary itself. But the relationship between light and space-time curvature goes even deeper. The speed of light itself determines how much space-time curves in response to matter and energy. Einstein's field equations, which describe this relationship mathematically, contain the speed of light as a fundamental parameter. If the speed of light were different, the universe would have an entirely different structure, with different relationships between matter, energy, space, and time. This intimate connection between light speed and space-time geometry suggests remarkable possibilities for manipulating the fabric of reality. If we could somehow create regions where light travels at different speeds, we might be able to create corresponding regions where space-time itself has different properties. A region of slower light might correspond to a region of increased space-time curvature, potentially creating artificial gravitational effects or temporal distortions. The concept of gravitational waves provides another fascinating example of how disturbances in space-time propagate at the speed of light. When massive objects accelerate, they create ripples in the fabric of space-time itself that travel outward at exactly the speed of light. These gravitational waves, first predicted by Einstein and finally detected in 2015 by the LIGO Gravitational Wave Observatory, represent direct evidence that space-time is a dynamic medium that can support wave motion. The detection of gravitational waves has opened up an entirely new window for studying the universe, allowing us to observe cosmic events like black hole mergers and neutron star collisions that would be invisible to conventional telescopes. But more importantly for our story, gravitational waves demonstrate that space-time itself can be manipulated and controlled, at least by sufficiently energetic astrophysical processes. If natural processes can create gravitational waves that reshape space-time, perhaps artificial processes could achieve similar effects on smaller scales. Theoretical proposals for space-time engineering include using rotating cylinders of ultra-dense matter to create closed time-like curves, constructing traversable wormholes with exotic matter, and generating Alcubierre warp bubbles that could enable faster-than-light travel by compressing and expanding space-time itself. All of these exotic space-time geometries share a common feature. They require the manipulation of matter and energy in ways that create unusual relationships between space, time, and the speed of light. In many cases, they require exotic matter with negative energy density, a form of matter that has never been observed but is not explicitly forbidden by the laws of physics. The challenge lies in understanding whether such exotic matter could actually exist and be controlled by advanced technology. But perhaps we do not need exotic matter to manipulate space-time in useful ways. The experiments that have slowed light to bicycle speeds suggest that we already possess some ability to alter the local relationship between electromagnetic fields and space-time geometry. When light slows down in a medium, it is not just the photons that are affected, but potentially the entire causal structure of space-time in that region. Consider what might happen if we could scale up slow light experiments to macroscopic dimensions. A large region where light travels at dramatically reduced speeds might also be a region where space-time itself has altered properties. Time might flow more slowly in such a region, creating a pocket of temporal distortion that could serve as a natural time machine. Objects entering this region would experience time differently than the surrounding universe, emerging to find that they had effectively traveled into the future. The relationship between electromagnetic fields and space-time geometry becomes even more intriguing when we consider the role of the quantum vacuum. According to quantum field theory, empty space is not truly empty, but is filled with virtual particles that constantly appear and disappear on timescales too brief for direct observation. These quantum fluctuations give the vacuum itself electromagnetic properties that affect the propagation of light. In extremely strong electromagnetic fields, these quantum vacuum effects can become macroscopic and measurable. Intense laser pulses can polarize the vacuum, creating virtual electron-positron pairs that modify the effective properties of empty space. Some theoretical calculations suggest that sufficiently powerful electromagnetic fields could alter the speed of light in vacuum itself, creating regions where photons travel faster or slower than the standard speed of light. Such vacuum modification could potentially be used to create artificial space-time geometries with exotic properties. A region where the vacuum has been modified to slow down light might also be a region where space-time curvature has been artificially enhanced. This could create localized gravitational effects without requiring massive objects, opening up possibilities for gravitational shielding, artificial gravity generation, or even the creation of microscopic black holes. The concept of negative refractive index materials, developed in recent years, provides a glimpse of how electromagnetic properties can be engineered to produce effects that seem to violate our intuitions about space and time. These metamaterials can bend light in directions that would be impossible with ordinary matter, creating effects like perfect lensing and electromagnetic cloaking. Some metamaterial designs have been shown to make light appear to travel backward in time over very short distances, at least from certain measurement perspectives. While these effects are currently limited to very specific wavelengths and very small distances, they demonstrate that the relationship between light and space-time is far more flexible than once believed. As our understanding of metamaterials and electromagnetic engineering continues to advance, we may develop the ability to create macroscopic regions where space-time itself has been engineered to have exotic properties. The holographic principle, emerging from string theory and black hole thermodynamics, suggests an even more fundamental connection between information, light, and the structure of space-time. This principle proposes that all the information contained within a volume of space can be encoded on its two-dimensional boundary, much like a hologram encodes three-dimensional information on a flat surface. If this principle is correct, then the three-dimensional space we experience might be a kind of projection from information encoded on a distant two-dimensional surface. This holographic view of reality suggests that space-time itself might be an emergent property arising from more fundamental information processing principles. Light, as the carrier of information through space-time, might play a crucial role in maintaining the consistency of this holographic projection. By manipulating the flow of information through controlled light interactions, we might be able to alter the local properties of the space-time projection itself. The study of space-time and its relationship to the speed of light reveals that the universe is far stranger and more malleable than our everyday experience suggests. Space and time are not fixed backdrops, but dynamic participants in cosmic evolution, responding to the presence of matter and energy by curving and warping in ways that guide the flow of causality itself. The speed of light serves as the fundamental constant that governs these interactions, determining how matter tells space-time how to curve, and how curved space-time tells matter how to move. As our technological capabilities continue to advance, we edge closer to the possibility of space-time engineering, using controlled electromagnetic fields and exotic matter to create artificial gravitational effects and temporal distortions. The experiments that have demonstrated dramatic control over light speed represent early steps toward this ultimate goal of manipulating the fabric of reality itself. Just as gravity warps space, light warps time. But could slowing light be the key to manipulating this relationship? At the edge of a black hole lies one of the most mysterious and profound boundaries in the universe, a point of no return called the event horizon, where even light, the fastest thing in existence, cannot escape the crushing grip of gravity. This invisible barrier represents the ultimate testing ground for our understanding of space, time, and the nature of reality itself. Here at the edge of oblivion, the normal rules of physics are pushed to their breaking point, and time itself seems to freeze in a cosmic dance that challenges everything we think we know about the flow of causality through the universe. The event horizon is not a physical surface like the ground beneath your feet or the wall of a building. It is a boundary in space-time itself, a point where the curvature of space becomes so extreme that the very geometry of reality is fundamentally altered. To understand what makes this boundary so special, we must first appreciate the incredible densities and gravitational fields that create black holes in the first place. A black hole forms when matter becomes compressed to such extraordinary density that its gravitational field becomes strong enough to prevent even light from escaping. The critical point occurs when the escape velocity, the speed needed to break free from the gravitational pull, reaches the speed of light itself. Since nothing can travel faster than light, nothing can escape from within this boundary. The size of the event horizon depends on the mass of the black hole, with more massive black holes having larger event horizons. For a black hole with the mass of our Sun, the event horizon would have a radius of about 3 kilometers. For the supermassive black holes found at the centers of galaxies, with masses millions or billions of times greater than the Sun, the event horizon can stretch across distances larger than our entire solar system. Yet regardless of size, all event horizons share the same fundamental property. They represent the point where the flow of time, as seen from the outside universe, appears to come to a complete stop. This temporal freezing effect emerges from the extreme gravitational time dilation that occurs near the event horizon. As we learned earlier, time runs slower in stronger gravitational fields, and the gravitational field near a black hole is the strongest in the universe. An outside observer, watching an astronaut fall toward a black hole, would see the astronaut's clocks running slower and slower as they approach the event horizon. Near the boundary itself, time dilation becomes so extreme that the astronaut appears to freeze in time, their image growing redder and dimmer, but never quite disappearing. From the astronaut's perspective, however, time continues to flow normally. They would pass through the event horizon in finite time, unaware that they have crossed the point of no return until it is too late. This creates one of the most profound paradoxes in physics. An event that takes finite time from one perspective takes infinite time from another perspective. The astronaut reaches the event horizon in their own reference frame, but from the outside universe's perspective, they never quite get there. This paradox becomes even more intriguing when we consider what happens to light at the event horizon. Photons trying to escape from just outside the event horizon become increasingly redshifted as they climb out of the black hole's gravitational well. Their wavelengths stretch to longer and longer values, their energy decreases, and their apparent frequency drops towards zero. From an outside observer's perspective, these photons take longer and longer to escape, until photons emitted exactly at the event horizon take infinite time to reach the outside universe. The behavior of light at the event horizon reveals something profound about the nature of space and time near black holes. The event horizon represents a null surface in space-time, meaning that light rays trying to escape travel along paths where the space-time interval is exactly zero. These photons exist in a strange liminal state, neither advancing nor retreating, frozen forever at the boundary between the known universe and the unknowable interior of the black hole. But what if we could somehow manipulate the speed of light itself near the event horizon? The experiments that have slowed light to bicycle speeds suggest that under the right conditions, the local speed of light can be dramatically altered. If we could create regions near a black hole where light travels at different speeds, we might be able to modify the location and properties of the event horizon itself. Consider the possibility of creating a bubble of slow light near a black hole. If light within this bubble travels at a dramatically reduced speed, the effective event horizon might shift outward, creating a larger region from which escape is impossible. Alternatively, a region of fast light might push the event horizon inward, creating a pathway for information or even matter to escape from regions that would normally be beyond the point of no return. These speculations may seem far-fetched, but they are grounded in the fundamental relationship between light speed and space-time geometry. The location of the event horizon is determined by the condition that the escape velocity equals the speed of light. If we could locally modify the speed of light, we would effectively be modifying the criteria for what constitutes the point of no return. The information paradox of black holes adds another layer of mystery to the behavior of light at the event horizon. According to quantum mechanics, information cannot be destroyed, yet anything falling into a black hole appears to be lost forever when the black hole eventually evaporates through Hawking radiation. This paradox has puzzled physicists for decades and has led to various proposed solutions, many of which involve subtle modifications to our understanding of how information behaves near event horizons. One proposed solution involves the concept of black hole complementarity, which suggests that information falling into a black hole exists in two complementary descriptions, one from the perspective of an outside observer, where the information remains frozen at the event horizon, and another from the perspective of an infalling observer, where the information crosses the event horizon and enters the black hole interior. These two descriptions are fundamentally incompatible, but never lead to observable contradictions because no single observer can verify both simultaneously. Another approach involves the holographic principle, which proposes that all the information within a black hole is actually encoded on its two-dimensional event horizon surface. In this view, the three-dimensional interior of the black hole is a kind of holographic projection of information stored on the event horizon boundary. Light plays a crucial role in this holographic encoding, carrying information about the black hole's interior to observers in the outside universe. Recent theoretical developments have suggested even more exotic possibilities for the behavior of light and information near event horizons. The firewall hypothesis proposes that quantum effects near the event horizon might create a wall of high-energy radiation that would incinerate anything trying to cross the boundary. This firewall would be invisible to outside observers, but would represent a fundamental breakdown of the smooth space-time geometry that classical general relativity predicts. The ER equals EPR conjecture, proposed by physicists Leonard Susskind and Juan Maldacena, suggests that quantum entanglement and traversable wormholes might be the same phenomenon viewed from different perspectives. If this conjecture is correct, then entangled particles might be connected by microscopic wormholes that could potentially be enlarged and stabilized to create pathways through spacetime. Such wormholes might provide a way to extract information from black hole interiors or even to escape from beyond the event horizon. These theoretical possibilities become even more intriguing when we consider the potential for artificial black hole creation and manipulation. While creating macroscopic black holes is far beyond our current technological capabilities, some theories suggest that microscopic black holes might be created in high-energy particle collisions or through the concentration of electromagnetic energy in very small regions. If microscopic black holes could be created and controlled, they might serve as laboratories for studying the behavior of light and time near event horizons. Such experiments could test our understanding of Hawking radiation, information preservation, and the relationship between quantum mechanics and gravity. They might even provide pathways for creating controlled temporal distortions that could be used for practical time manipulation. The concept of white holes, theoretical objects that represent the time reverse of black holes, adds another dimension to our understanding of event horizons and their relationship to time travel. While black holes have event horizons that prevent anything from escaping, white holes would have event horizons that prevent anything from entering. Matter and energy would pour out of white holes, but could never fall in, creating fountains of space-time that might serve as sources of negative entropy. If white holes could exist, they might provide natural time machines, allowing travelers to emerge in the past by following paths that connect black hole and white hole event horizons through hypothetical Einstein-Rosen bridges or wormholes. The light escaping from white holes would carry information about future events back into the past, potentially creating causal loops and temporal paradoxes. The study of analog black holes in laboratory settings has provided new insights into the behavior of light near event horizons. These analog systems use flowing fluids, moving optical media, or Bose-Einstein condensates to create conditions where sound waves or light pulses experience effective event horizons. While these systems do not involve actual gravitational effects, they exhibit many of the same mathematical properties as real black holes, including analog Hawking radiation and information loss phenomena. Recent experiments with analog black holes have demonstrated that information can indeed be preserved in the analog Hawking radiation, suggesting that the information paradox might have a resolution that does not require exotic physics or fundamental modifications to quantum mechanics. These results hint that the apparent loss of information in black holes might be an artifact of our limited ability to decode the subtle correlations in Hawking radiation, rather than a fundamental breakdown of physical law. The possibility that black holes might not be the absolute barriers to escape that they appear to be has profound implications for time travel and information processing. If information can leak out of black holes through subtle quantum correlations, then perhaps the event horizon is not as absolute a boundary as once believed. The manipulated light experiments that have achieved dramatic control over electromagnetic propagation might provide clues for how to extract information from regions that appear to be causally disconnected from the outside universe. Advanced civilizations might develop technologies for manipulating the properties of event horizons themselves, creating controllable regions of extreme space-time curvature that could serve as gateways for information transfer, or even travel between different regions of space-time. Such technologies might involve the precise control of electromagnetic fields near black holes, the creation of exotic matter with negative energy density, or the manipulation of quantum vacuum fluctuations to modify the local properties of space-time. The event horizon represents the ultimate frontier in our quest to understand the relationship between light, time, and the fabric of reality. Here, at the edge of black holes, the normal flow of causality breaks down. Time appears to stop, and light itself becomes trapped in an eternal dance with gravity. Yet even this seemingly absolute barrier might not be insurmountable. As our understanding of quantum mechanics, electromagnetic manipulation, and space-time engineering continues to advance, we may discover that even the event horizon can be transcended. The mysteries of black holes and their event horizons continue to challenge our deepest understanding of physics and reality. They represent natural laboratories where the most extreme conditions in the universe test the limits of our theories and push us toward new insights about the nature of space, time, and information. As we learn to manipulate light in increasingly sophisticated ways, we edge closer to understanding how even these ultimate barriers might be overcome. At the edge of a black hole, time seems to freeze. Could slowing light down allow us to traverse this boundary, to explore time itself? The quest to understand whether time travel is possible has led physicists to explore some of the most exotic and mind-bending concepts in theoretical physics. Far from the realm of science fiction, these investigations are grounded in rigorous mathematics and the fundamental laws of nature, revealing that the universe may be far stranger and more malleable than our everyday experience suggests. From traversable wormholes that could connect distant regions of space-time to exotic propulsion systems that could outrun light itself, the theoretical landscape of time travel encompasses possibilities that challenge our deepest assumptions about the nature of reality. Perhaps the most famous and widely studied theoretical time machine is the traversable wormhole, a hypothetical tunnel through space-time that could connect two distant regions of the universe or even two different moments in time. The mathematical foundation for wormholes emerges naturally from Einstein's field equations, which describe how matter and energy curve the fabric of space-time. While Einstein himself was skeptical that such structures could actually exist, subsequent theoretical work has shown that wormholes are not forbidden by the laws of physics, though they would require exotic forms of matter to remain stable and traversable. The key challenge in creating a traversable wormhole lies in preventing it from collapsing before anything can pass through. The natural tendency of space-time curvature is to create regions that either expand outward or contract inward, like the event horizons of black holes. To keep a wormhole open, physicists have determined that exotic matter with negative energy density would be required. This exotic matter would need to violate what is known as the null energy condition, creating regions where the energy density is actually negative rather than positive. While no macroscopic examples of negative energy density have ever been observed, quantum field theory does predict that such exotic matter can exist on microscopic scales. The Casimir effect, where two parallel metal plates placed very close together experience an attractive force due to quantum vacuum fluctuations, demonstrates that regions of negative energy density can indeed be created in laboratory conditions. The challenge lies in scaling up these quantum effects to macroscopic dimensions and maintaining them for extended periods. Recent advances in our understanding of quantum mechanics and electromagnetic manipulation suggest that exotic matter might not be as exotic as once believed. The experiments that have slowed light to bicycle speeds involve creating quantum states of matter that have highly unusual electromagnetic properties. Perhaps these same techniques could be extended to create the negative energy densities required for wormhole construction and stabilization. Another promising approach to time travel involves the Alcubierre warp drive, proposed by physicist Miguel Alcubierre in 1994. Rather than moving a spacecraft through space at faster than light speeds, the Alcubierre drive would manipulate space-time itself, contracting space in front of the ship and expanding space behind it. The spacecraft would ride in a bubble of flat space-time that surfs on this wave of compressed and expanded space, potentially allowing effective faster-than-light travel without the ship itself ever exceeding the speed of light locally. The mathematical elegance of the Alcubierre drive lies in its respect for the fundamental principles of relativity, while still allowing for apparent violations of the cosmic speed limit. Since the spacecraft never moves faster than light relative to its local space-time environment, it avoids the infinite energy requirements and causality violations that would arise from conventional faster-than-light travel. However, like traversable wormholes, the Alcubierre drive requires exotic matter with negative energy density to create the necessary space-time distortions. The energy requirements for an Alcubierre drive are truly astronomical, initially calculated to require more negative energy than exists in the observable universe. However, subsequent refinements to the design have dramatically reduced these energy requirements. By optimizing the shape of the warp bubble and the distribution of exotic matter, theorists have brought the energy requirements down to levels that might be achievable by advanced civilizations, though still far beyond our current technological capabilities. The connection between faster-than-light travel and time travel becomes apparent when we consider the relativity of simultaneity. In Einstein's special theory of relativity, events that appear simultaneous to one observer may occur at different times for another observer, moving at high velocity relative to the first. If a spacecraft could travel faster than light using an Alcubierre drive, it could potentially arrive at its destination before it left, creating a closed time-like curve that would allow for travel into the past. Closed time-like curves represent another fascinating class of theoretical time machines. These are paths through space-time that loop back on themselves, allowing a traveler to return to their own past. While such curves might seem to violate causality, they are actually consistent solutions to Einstein's field equations under certain exotic conditions. The challenge lies in creating the extreme space-time curvatures necessary to bend time back on itself. One of the most studied examples of closed time-like curves is the Gödel universe, a cosmological solution discovered by mathematician Kurt Gödel in 1949. This theoretical universe contains rotating matter that creates closed time-like curves throughout all of space. While our actual universe does not appear to have the properties of a Gödel universe, the mathematical existence of such solutions demonstrates that time travel is not fundamentally forbidden by the laws of general relativity. The Tipler cylinder represents another theoretical time machine that could potentially be constructed by sufficiently advanced technology. Proposed by physicist Frank Tipler, this device would consist of an infinitely long cylinder of ultra-dense matter rotating at nearly the speed of light. The rotation would drag space-time around with it, creating frame dragging effects that could generate closed time-like curves in the surrounding region. While an infinitely long cylinder is obviously impossible to construct, finite versions might still produce useful time travel effects. Recent theoretical work has explored the possibility of creating time machines using cosmic strings, hypothetical one-dimensional defects in space-time that might have formed during the early universe. If cosmic strings exist and could be manipulated, they might provide a more accessible pathway to time travel than the exotic matter requirements of wormholes or Alcubierre drives. Two cosmic strings moving past each other at high velocity could create a region of space-time where closed time-like curves become possible. The relationship between quantum mechanics and time travel adds another layer of complexity to these theoretical models. Quantum effects near time machines could potentially prevent paradoxes from occurring through mechanisms like the Novikov self-consistency principle, which suggests that the universe would naturally arrange itself to prevent paradoxical situations from arising. Alternatively, quantum mechanics might allow for multiple, consistent histories, enabling time travel without logical contradictions. The many worlds interpretation of quantum mechanics offers yet another perspective on time travel possibilities. If every quantum measurement causes reality to branch into multiple parallel universes, then time travel might involve moving between different branches of the quantum multiverse, rather than traveling through time within a single universe. This could potentially resolve the grandfather paradox and other causality issues by allowing changes to the past to create new timeline branches without affecting the original timeline. The holographic principle emerging from string theory and black hole physics suggests that time travel might be possible through the manipulation of information rather than matter. If the three-dimensional reality we experience is actually a holographic projection from information encoded on a two-dimensional surface, then perhaps time travel could be achieved by manipulating this underlying information structure. Light, as the carrier of information through space-time, might play a crucial role in such information-based time travel mechanisms. Recent developments in quantum field theory have revealed new possibilities for time travel through the manipulation of quantum vacuum fluctuations. The quantum vacuum, far from being empty, is filled with virtual particles that constantly appear and disappear on timescales too brief for direct observation. These quantum fluctuations give rise to phenomena like the Casimir effect and vacuum polarization in strong electromagnetic fields. Some theoretical proposals suggest that sufficiently intense electromagnetic fields could modify the properties of the quantum vacuum itself, potentially creating regions where the effective speed of light is altered or where exotic matter with negative energy density spontaneously appears. If such vacuum engineering becomes possible, it might provide a pathway to time travel that does not require the mining or creation of exotic matter from other sources. The connection between light manipulation and time travel becomes even more intriguing when we consider the role of electromagnetic fields in space-time geometry. Maxwell's equations, which describe the behavior of electromagnetic fields, are intimately connected to Einstein's field equations through the stress-energy tensor. Changes in electromagnetic field configurations can alter the curvature of space-time, potentially creating the exotic geometries required for time travel. The experiments that have demonstrated dramatic slowing of light involve creating highly coherent quantum states of matter that interact with electromagnetic fields in unusual ways. If these techniques could be scaled up and extended, they might provide a mechanism for creating macroscopic regions of altered space-time geometry without requiring exotic matter from external sources. The slow light itself might serve as the exotic matter needed to stabilize wormholes or power Alcubierre drives. Consider the possibility of creating a large-scale analog of the slow light experiments, where electromagnetic fields are used to create a region of space-time with dramatically altered causal structure. Such a region might exhibit properties similar to the theoretical time machines we have discussed, allowing for controlled manipulation of the flow of time without requiring the extreme conditions found near black holes or neutron stars. The energy requirements for macroscopic time machines remain a significant challenge, but recent advances in energy storage and electromagnetic field generation suggests that these requirements might not be as insurmountable as once believed. Superconducting magnetic energy storage systems can already store enormous amounts of energy in electromagnetic fields, and advances in materials science continue to push the boundaries of what is possible with field generation and control. Fusion energy, once it becomes practical, could provide the enormous power sources needed to create and maintain exotic space-time geometries. The energy density of nuclear fusion approaches levels that could potentially create measurable space-time curvatures, especially when combined with sophisticated electromagnetic field configurations designed to focus and amplify these effects. The development of room-temperature superconductors and advanced metamaterials opens up new possibilities for creating and controlling electromagnetic fields with unprecedented precision. These technologies might enable the creation of field configurations that can alter the local properties of space-time in ways that were previously impossible, potentially providing pathways to time travel that do not require exotic matter or astronomical energy expenditures. As our understanding of quantum mechanics, general relativity, and electromagnetic field theory continues to advance, the theoretical models of time travel become increasingly sophisticated and potentially achievable. While we are still far from constructing practical time machines, the mathematical foundations for such devices are becoming increasingly well understood, and the technological prerequisites are becoming increasingly accessible. The quest to bend the flow of time through the manipulation of light and electromagnetic fields represents one of the most ambitious goals in theoretical physics. It challenges us to push the boundaries of our understanding of space, time, and causality, while opening up possibilities that could fundamentally transform our relationship with the universe itself. Time travel may sound like science fiction, but the theories are grounded in real science. Could the key to bending time lie in our ability to manipulate light? The possibility of manipulating the speed of light on a cosmic scale opens up scenarios so profound and far-reaching that they challenge our most fundamental understanding of how the universe works. If we could somehow alter the speed of light, not just in small laboratory experiments, but across vast regions of space, the consequences would ripple through every aspect of physics, from the behavior of individual atoms to the evolution of galaxies themselves. Such changes would reshape the very fabric of reality, altering the laws that govern matter, energy, space, and time in ways that could fundamentally transform the nature of existence itself. To appreciate the magnitude of these potential changes, we must first recognize that the speed of light is not merely another physical constant, like the mass of an electron or the charge of a proton. Rather, it is deeply woven into the mathematical structure of all physical laws, serving as the fundamental conversion factor between space and time, matter and energy, electric and magnetic fields. Every equation in physics, from quantum mechanics to general relativity, contains the speed of light as a crucial parameter that determines how different phenomena relate to one another. Consider what would happen if the speed of light was suddenly reduced across a large region of space. The immediate consequence would be a dramatic alteration in the causal structure of that region. Events that were previously causally connected, able to influence one another through the exchange of light signals, would become causally disconnected if the reduced light speed made such communication impossible within the available time. The boundary of this slow light region would become a kind of causal horizon, separating the interior from the rest of the universe in ways that could fundamentally alter the flow of information and causality. Within such a slow light region, the very nature of matter itself would be transformed. The electromagnetic forces that hold atoms together operate at the speed of light, binding electrons to nuclei through the constant exchange of virtual photons. If light speed were dramatically reduced, these electromagnetic interactions would become sluggish and weak, potentially causing atoms to expand to enormous sizes, or even disintegrate entirely. Chemical bonds, which depend on the electromagnetic forces between atoms, would be similarly affected, possibly making complex chemistry impossible within the slow light zone. The implications for living organisms would be catastrophic. Biological processes, from the firing of neurons to the replication of DNA, depend critically on electromagnetic interactions operating at light speed. A significant reduction in light speed could cause nervous systems to malfunction, proteins to unfold, and cellular machinery to grind to a halt. Life as we know it might be impossible within regions of dramatically slowed light, creating sterile zones where only the most fundamental particles could exist in stable configurations. But the effects would extend far beyond individual atoms and molecules. The propagation of electromagnetic waves, including radio waves, microwaves, and all forms of electromagnetic radiation, would be slowed proportionally. This would create massive disruptions in any technological civilization within or near the affected region. Communication systems would fail as radio signals crawled at reduced speeds. Power grids would malfunction as the alternating currents that carry electrical energy would be limited by the reduced speed of electromagnetic propagation. Gravitational effects would also be altered in subtle but important ways. While gravity itself does not travel at the speed of light in the same way that electromagnetic radiation does, Einstein's field equations contain the speed of light as a fundamental parameter. Changes in light speed could potentially alter the relationship between matter, energy, and space-time curvature, leading to modifications in gravitational fields and orbital mechanics. The energy content of the electromagnetic field itself would be affected by changes in light speed. According to Einstein's famous equation, E equals mc squared, energy and mass are related through the speed of light squared. If light speed were reduced, the energy equivalent of a given mass would be dramatically decreased. This could have profound implications for nuclear processes, stellar evolution, and the overall energy balance of the universe. Stars, those cosmic furnaces that power the universe through nuclear fusion, would be particularly vulnerable to changes in light speed. The fusion reactions that occur in stellar cores depend on a delicate balance between gravitational compression and radiation pressure. The photons produced by fusion reactions carry energy outward from the core, creating the radiation pressure that prevents stars from collapsing under their own gravity. If light speed were reduced, these photons would carry less energy and take longer to escape from the stellar interior, potentially causing stars to become unstable or collapse entirely. The cosmic microwave background radiation, the afterglow of the Big Bang that fills all of space, would also be affected by changes in light speed. This ancient light has been traveling through the universe for nearly 14 billion years, carrying information about the early universe and the fundamental parameters of cosmology. If light speed were altered in different regions of space, the cosmic microwave background would show corresponding distortions and anomalies that could reveal the presence and extent of these modified regions. On larger scales, the expansion of the universe itself could be affected by changes in light speed. The Hubble constant, which describes the rate of cosmic expansion, is intimately connected to fundamental physical constants, including the speed of light. Alterations in light speed could potentially alter the apparent rate of cosmic expansion, creating regions where space seems to expand faster or slower than expected, based on standard cosmological models. The formation and evolution of large-scale structures in the universe, such as galaxy clusters and cosmic filaments, depend on the intricate interplay between gravity, dark matter, and electromagnetic radiation. Changes in light speed could disrupt this delicate balance, potentially preventing the formation of galaxies and stars in affected regions, or causing existing structures to evolve in unexpected ways. But perhaps the most profound implications of slowing light would involve the nature of time itself. As we have explored throughout our journey, The speed of light serves as the fundamental link between space and time in Einstein's theories of relativity. Regions of slowed light might also be regions of altered temporal flow, creating pockets of space where time moves at different rates relative to the surrounding universe. Such temporal distortions could have cascading effects on causality and the flow of information through the universe. Events within slow light regions might appear to unfold in slow motion to outside observers, while inhabitants of these regions might perceive the external universe as accelerating past them at tremendous speeds. The boundary between normal space and slow light regions could become a temporal interface where different rates of time meet and interact in complex ways. The second law of thermodynamics, which describes the inevitable increase of entropy over time, might also be affected by changes in light speed. Entropy increase is fundamentally connected to the irreversible flow of information and energy through physical systems. If light speed governs the rate at which information can propagate, then changes in light speed might alter the rate at which entropy increases, potentially creating regions where thermodynamic processes occur at different rates or even in reverse. Consider the possibility of creating artificial regions of slowed light as a form of cosmic engineering. Advanced civilizations might use such techniques to create protective barriers around their star systems, regions where time flows slowly and external threats are slowed to manageable speeds. Alternatively, they might use fast light regions to accelerate natural processes, speeding up stellar evolution or planetary formation for their own purposes. The energy requirements for creating macroscopic regions of altered light speed would be enormous, likely requiring technologies far beyond our current capabilities. However, the potential benefits could justify such massive investments. A civilization capable of manipulating light speed across cosmic distances would essentially have control over the flow of time itself, enabling them to accelerate or decelerate processes according to their needs and desires. Such cosmic-scale light manipulation might also provide a defense against existential threats like gamma-ray bursts or supernovae. By creating barriers of slowed light around vulnerable regions, civilizations could potentially deflect or absorb deadly radiation that would otherwise sterilize entire star systems. The slowed light regions would act like temporal shields, giving inhabitants time to prepare for or avoid cosmic catastrophes. The detection of artificially created slow light regions could serve as a signature of advanced technological civilizations. Astronomical observations might reveal anomalous regions where light propagates at unexpected speeds, where stellar processes occur at unusual rates, or where the normal relationships between electromagnetic phenomena are altered. Such observations could provide the first evidence of cosmic-scale engineering by intelligence far in advance of our own. But the implications extend beyond practical applications to fundamental questions about the nature of reality itself. If the speed of light can be altered, then the apparently fixed constants of nature might be more malleable than we have assumed. This could open up possibilities for modifying other fundamental parameters of physics, potentially allowing advanced civilizations to create custom regions of space-time with properties optimized for their specific needs. The quantum mechanical aspects of light propagation add another layer of complexity to these scenarios. Quantum field theory describes the vacuum of space as filled with virtual particles and fields that give rise to phenomena like the Casimir effect and vacuum polarization. Changes in light speed could potentially alter these quantum vacuum properties, creating regions where new particles can be spontaneously created or where existing particles behave in unexpected ways. The relationship between consciousness and physical reality, already mysterious in our normal universe, could become even more complex in regions of altered light speed. If consciousness depends on electromagnetic processes in the brain operating at specific speeds, then changes in light speed could potentially alter states of consciousness or enable new forms of awareness that are impossible under normal conditions. As we contemplate these far-reaching implications, we begin to appreciate that the speed of light is not merely a limit on how fast things can move, but is actually a fundamental parameter that determines the very nature of reality itself. The experiments that have demonstrated control over light speed in small laboratory settings hint at possibilities that could ultimately reshape the universe on the largest scales. The power to slow light is the power to reshape the fundamental structure of space-time, to alter the flow of time itself, and to create regions where the normal laws of physics are suspended or modified according to our will. While such capabilities remain far beyond our current technology, they represent the ultimate frontier in our quest to understand and control the universe around us. If slowing light could change the flow of time, what would it mean for the universe at large? Could time itself be a malleable concept, subject to the forces of light? As we stand at the threshold of the 21st century's greatest discoveries, the dream of controlling time through the manipulation of light seems to hover tantalizingly between the realm of science fiction and the edge of scientific possibility. The experiments that have already slowed light to bicycle speeds, stopped it completely, and restarted it without loss of information represent just the first tentative steps toward what could become humanity's greatest technological achievement. The question is no longer whether the laws of physics permit time travel, but rather whether we will develop the knowledge, technology, and wisdom necessary to harness these fundamental forces for our benefit. The trajectory of scientific progress over the past century gives us reason for both optimism and caution. In 1900, the idea that we could split atoms, manipulate genes, or send information instantly around the globe would have seemed as impossible as time travel seems today. Yet each of these achievements required not just theoretical breakthroughs, but also the development of entirely new technologies, materials, and engineering techniques. The path from understanding to implementation often spans decades or even centuries, requiring sustained effort across multiple generations of researchers and engineers. Today's cutting-edge research in quantum optics and metamaterials provides glimpses of what might be possible in the future of light manipulation. Scientists are already creating materials with negative refractive indices that bend light in directions that would be impossible with ordinary matter. They are developing programmable metamaterials whose electromagnetic properties can be dynamically controlled using electrical signals. They are crafting photonic crystals that can trap light in incredibly small volumes and manipulate its propagation in precise ways. These advances suggest that we are rapidly approaching a level of electromagnetic control that was unimaginable just a few decades ago. The same techniques that allow us to create invisibility cloaks and perfect lenses might eventually be scaled up to create macroscopic regions where light behaves in fundamentally different ways. The challenge lies in bridging the gap between laboratory demonstrations involving single photons or microscopic structures and practical devices that can manipulate light across human scale or even cosmic scale dimensions. Quantum computing represents another promising avenue for advancing our control over light and information. Quantum computers use the quantum properties of light and matter to perform calculations that would be impossible with classical computers. As these systems become more powerful and sophisticated, they might enable us to solve the complex optimization problems involved in designing electromagnetic field configurations for time manipulation. A sufficiently advanced quantum computer might even be able to simulate the behavior of light in exotic space-time geometries, helping us understand how to create practical time machines. The development of room temperature superconductors could revolutionize our ability to generate and control powerful electromagnetic fields. Current superconducting technologies require expensive cooling systems that limit their practical applications, but room temperature superconductors would enable the creation of powerful magnetic fields with minimal energy expenditure. Such materials could make it feasible to create and maintain the intense electromagnetic field configurations needed for macroscopic light manipulation and space-time engineering. Fusion energy, when it finally becomes practical and abundant, could provide the enormous power sources needed to create artificial space-time geometries. The energy densities achievable through fusion reactions approach levels that could create measurable curvatures in space-time, especially when focused and amplified through sophisticated electromagnetic field configurations. A civilization with abundant fusion energy and advanced electromagnetic control might be able to create the conditions necessary for practical time travel without requiring exotic matter or astronomical energy expenditures. Advances in materials science continue to push the boundaries of what is possible with electromagnetic field generation and control. Researchers are developing new superconducting materials that can maintain coherent quantum states at higher temperatures and for longer periods. They are creating metamaterials with properties that can be dynamically reconfigured using external stimuli. They are engineering nanostructures that can manipulate light with unprecedented precision and efficiency. Perhaps most intriguingly, the emerging field of programmable matter promises materials that can reconfigure their properties and structure in real time according to external commands. Such materials might eventually enable the creation of adaptive spacetime engineering systems that could dynamically adjust their electromagnetic field configurations to maintain optimal conditions for time manipulation. The ability to program matter at the atomic level could provide the fine-grained control necessary to create and stabilize exotic space-time geometries. The intersection of artificial intelligence and physics could accelerate progress toward practical time travel in unexpected ways. Machine learning algorithms are already being used to discover new materials with desired properties, optimize electromagnetic field configurations, and solve complex physics problems that would be intractable for human researchers. An artificial intelligence system specifically designed to explore the possibilities for light manipulation and space-time engineering might discover approaches that would take human scientists centuries to develop. But the technical challenges, while formidable, may pale in comparison to the conceptual and philosophical questions that practical time travel would raise. The ability to manipulate the flow of time would fundamentally alter human society, economics, and ethics in ways that are difficult to predict or prepare for. Questions of causality, free will, and the nature of existence itself would take on new urgency as time travel transitions from theoretical possibility to practical reality. Consider the social implications of controlled time dilation technology. If some people could spend time in slow time regions where they age more slowly than others, how would society handle the resulting inequalities in lifespan and experience? Would access to time manipulation become a privilege reserved for the wealthy and powerful, or would it be treated as a fundamental human right? How would legal systems handle crimes committed by people who can manipulate their relationship to time? The economic implications are equally profound. If manufacturing processes could be accelerated by placing them in fast time regions, or if research and development could be conducted in slow time regions where scientists have effectively unlimited time to work on problems, the competitive advantages would be enormous. Entire industries might be transformed by the ability to manipulate the flow of time according to economic needs and priorities. The possibility of backward time travel raises even more complex questions about the nature of causality and free will. If changes to the past can affect the present, do we truly have free will, or are our choices predetermined by future interventions? How would society handle the knowledge that the past might be mutable and subject to revision by time travelers from the future? These philosophical challenges highlight the need for careful ethical consideration as time travel research progresses. The development of time manipulation technology should be guided by principles that protect human dignity, preserve the integrity of causality, and ensure that the benefits are shared equitably across all of humanity. International cooperation and oversight may be necessary to prevent the misuse of time travel technology for military, political, or economic domination. But perhaps the greatest challenge lies in developing the wisdom and maturity necessary to handle such power responsibly. The ability to manipulate time would represent the ultimate technological capability, surpassing even the power to create or destroy matter and energy. A civilization that achieves mastery over time would need to have also achieved a corresponding level of ethical and spiritual development to avoid destroying itself or others through careless or malicious use of temporal manipulation. The search for extraterrestrial intelligence might provide clues about how advanced civilizations handle the development of time manipulation technology. If other intelligent species have achieved the ability to control the flow of time, their approaches to managing this capability could serve as valuable guidance for our own development. Conversely, the apparent absence of obvious time travelers from the future visiting our present might suggest either that time travel remains impossible, that advanced civilizations choose not to interfere with less developed species, or that the ethical constraints on time travel are so strong that it is rarely used. Recent developments in theoretical physics continue to expand our understanding of what might be possible with advanced time manipulation technology. String theory suggests that our familiar three-dimensional space might be just one slice of a higher dimensional reality, opening up possibilities for time travel through extra-dimensional shortcuts. Loop quantum gravity proposes that space and time themselves might have a granular structure at the smallest scales, potentially providing new avenues for temporal manipulation through quantum mechanical effects. The holographic principle, emerging from black hole physics and string theory, suggests that the information content of any region of space might be encoded on its boundary surface. If this principle is correct, then time travel might be achievable through the manipulation of information rather than matter, potentially reducing the energy requirements and technical challenges involved in creating practical time machines. Quantum error correction, developed for quantum computing applications, might provide techniques for maintaining the stability and coherence of exotic spacetime geometries. Just as quantum error correction allows quantum computers to perform reliable calculations. Despite the fragility of quantum states, similar techniques might enable the creation of stable time machines that can maintain their unusual properties despite environmental disturbances and quantum fluctuations. As we look toward the future, the development of time travel technology seems to require advances across multiple scientific and technological frontiers simultaneously. Progress in quantum mechanics, general relativity, materials science, energy generation, electromagnetic control, artificial intelligence, and philosophical understanding will all be necessary to achieve practical mastery over the flow of time. The timeline for these developments is difficult to predict, but historical precedent suggests that the most transformative technologies often develop more rapidly than initially expected once the fundamental principles are understood. The transition from theoretical understanding to practical application can be accelerated by focused research efforts, adequate funding, and international collaboration among the world's brightest minds. Perhaps most importantly, the quest to control time through light manipulation represents more than just a technological goal. It embodies humanity's deepest desire to transcend the limitations that constrain our existence, to explore the farthest reaches of possibility, and to understand our place in the vast cosmic story that unfolds around us. Whether or not we ultimately achieve practical time travel, the journey toward this goal will undoubtedly lead to discoveries and insights that transform our understanding of reality itself. The experiments that have already demonstrated remarkable control over the speed of light represent the first steps on this incredible journey. As our knowledge deepens and our capabilities expand, we move ever closer to answering the ultimate question that has driven our exploration from the beginning. In a universe where light can be slowed, stopped, and restarted at will, where space-time can be curved and twisted by electromagnetic fields, and where the quantum realm offers pathways beyond our ordinary understanding of causality, the dream of traveling through time may finally be within our grasp. While time travel remains a distant dream, the future of science offers endless possibilities. Could slowing light lead to breakthroughs that change the way we experience time? As our journey through the mysteries of light and time draws to a close, we find ourselves back where we began, standing beneath a canopy of stars that have witnessed the birth and death of countless worlds across billions of years. Each point of light in the night sky carries with it the story of time itself, photons that have traveled unimaginable distances to reach our eyes, connecting us to the deepest mysteries of existence. The same starlight that inspired ancient philosophers to wonder about the nature of reality continues to illuminate new possibilities for understanding and perhaps even controlling the flow of time itself. Throughout our exploration, we have discovered that the relationship between light and time is far more profound and intimate than our everyday experience might suggest. We have learned that the speed of light is not merely a cosmic speed limit, but the fundamental constant that weaves together the fabric of space and time into a unified whole. We have seen how this constant governs everything from the behavior of subatomic particles to the evolution of galaxies, serving as the ultimate arbiter of causality and the flow of information through the universe. The experiments that have slowed light to bicycle speeds, stopped it completely, and restarted it without loss of information represent more than just technical achievements. They are glimpses into a future where humanity might possess unprecedented control over the fundamental forces that shape reality. These early demonstrations of light manipulation hint at possibilities that extend far beyond the laboratory, suggesting that the dream of time travel might not be forever confined to the realm of science fiction. We have explored how the quantum nature of light opens up pathways to temporal manipulation that go far beyond the classical physics of relativity. In the strange world of quantum mechanics, where particles can exist in multiple states simultaneously and influence each other instantaneously across vast distances, the boundaries between past, present, and future become blurred in ways that challenge our most basic assumptions about the nature of time itself. The theoretical foundations for time travel through light manipulation rest on solid scientific ground, emerging naturally from Einstein's theories of relativity and the mathematical structure of quantum field theory. From traversable wormholes that could connect distant regions of space-time to Alcubierre drives that could enable faster-than-light travel by manipulating the fabric of space itself, the possibilities are as intriguing as they are challenging to realize. Yet perhaps the most profound revelation of our journey has been the recognition that time itself might be far more malleable than we ever imagined. The experiments that have demonstrated dramatic control over the speed of light suggest that the apparent fixity of temporal flow might be an illusion born of our limited perspective. In a universe where light can be slowed, stopped, and manipulated at will, the dream of controlling time itself seems less like fantasy and more like destiny. The implications of achieving practical time travel through light manipulation extend far beyond individual convenience or curiosity. Such capabilities could fundamentally transform human civilization, offering solutions to some of our greatest challenges, while simultaneously presenting new ethical and philosophical dilemmas that we are only beginning to contemplate. The power to manipulate time would be the ultimate technological achievement, surpassing even our ability to harness nuclear energy or manipulate genetic information. But with great power comes great responsibility, and the development of time manipulation technology would require a corresponding evolution in human wisdom and ethical understanding. The ability to alter the flow of time could easily be misused for selfish or destructive purposes, making it crucial that such capabilities be developed within frameworks that prioritize the common good and the preservation of human dignity. As we look toward the future, the path to practical time travel appears to require advances across multiple scientific frontiers simultaneously. Progress in quantum mechanics, materials science, electromagnetic control, energy generation, and computational power will all be necessary to bridge the gap between current laboratory demonstrations and practical time manipulation devices. The timeline for these developments remains uncertain, but the rapid pace of technological progress suggests that what seems impossible today might become routine within the span of a few generations. The search for extraterrestrial intelligence might provide valuable insights into how advanced civilizations handle the development of time manipulation technology. If other intelligent species have achieved mastery over time, their approaches to managing this capability could serve as crucial guidance for our own development. Alternatively, the apparent absence of obvious time travelers from the future might suggest important constraints or ethical principles that govern the use of temporal manipulation capabilities. Recent theoretical developments continue to expand our understanding of what might be possible with advanced control over light and time. String theory, loop quantum gravity, the holographic principle, and other cutting-edge concepts in theoretical physics all suggest that reality might be far stranger and more malleable than our current understanding suggests. These emerging theories hint at new pathways to time travel that might require less exotic matter or energy than previous approaches. The quantum revolution that began in the early 20th century continues to reveal new possibilities for manipulating reality at its most fundamental level. Quantum computing, quantum communication, and quantum control techniques are rapidly advancing, opening up new avenues for exploring the relationship between information, consciousness, and the flow of time. As our ability to manipulate quantum systems becomes more sophisticated, we edge closer to understanding how these microscopic effects might be scaled up to create macroscopic alterations in space-time itself. But perhaps the greatest mystery of all lies not in the technical challenges of creating time machines, but in understanding the deeper nature of time itself. Is time a fundamental aspect of reality? Or is it an emergent property arising from more basic physical processes? Does consciousness play a role in defining the flow of time? Or is temporal passage purely objective? These questions touch on some of the deepest philosophical problems in science, and may require entirely new ways of thinking about the nature of existence. As we contemplate these profound mysteries, we are reminded that the universe is vast beyond imagination and filled with wonders that we are only beginning to understand. The light from distant stars carries messages across cosmic time, connecting us to events that occurred billions of years ago and will continue to unfold billions of years into the future. In this context, our brief existence on Earth represents just one moment in an eternal cosmic story. Yet it is a moment filled with the potential to unlock secrets that could transform our understanding of everything. The quest to manipulate light and control time represents humanity at its best, driven by curiosity, creativity, and the desire to transcend the limitations that constrain our existence. Whether or not we ultimately achieve practical time travel, the journey toward this goal will undoubtedly lead to discoveries and insights that enrich our understanding of the universe and our place within it. So as we rest beneath the ancient light of distant stars, we can take comfort in knowing that we are part of something larger than ourselves, participants in a cosmic story that spans space and time in ways that challenge our imagination. The photons that left those stars eons ago have traveled across the galaxy to reach us tonight, carrying with them the promise that even the most fantastic dreams might one day become reality. In the gentle darkness of night, surrounded by the eternal dance of light and time, we can embrace the unknown with wonder and anticipation. The mysteries we have explored tonight may seem impossibly complex and distant, yet they are intimately connected to the deepest questions about who we are and where we are going as a species. The same curiosity that drives children to ask why the sky is blue or how far away the stars are continues to motivate scientists and dreamers to push the boundaries of what is possible. Time is indeed a mystery, and light is the messenger that guides us through it. As we close our eyes and let our minds wander through the cosmos, we can imagine a future where humanity has learned to slow light down, to bend space-time to our will, and to navigate through time as easily as we navigate through space. Whether that future is decades, centuries, or millennia away, it represents a destiny worthy of our greatest efforts and highest aspirations. Until that day arrives, we can rest peacefully under the stars, knowing that we are surrounded by mysteries waiting to be solved, discoveries waiting to be made, and possibilities waiting to be explored. The answers to the universe's greatest questions are always just beyond the horizon, beckoning us forward into an adventure that has no end. Time is a mystery, and light is the messenger that guides us through it. As we rest beneath the stars, we embrace the unknown, knowing that the answers to the universe's greatest questions are always just beyond the horizon.